Almost 340 years after Isaac Newton's formulation of the universal law of gravity, and 111 years after Albert Einstein's general theory of relativity, we understand gravity quite well as one of the four fundamental forces of nature. And yet, it continues to mystify us as an exquisitely subtle phenomenon as well as for its universality. One of the high profile physicists who studies gravity among other subjects is Professor Claudia de Rahm. Dr. de Rahm is a theoretical physicist at Imperial College London who specializes in quantum field theory, gravity, gravitational waves, cosmology, particle physics, numerical simulations, and theoretical mathematical physics. Lately, she has also become a much sought after speaker at conferences and media conversations. She spoke to MCR from London. On a personal note, I'm in the midst of writing a book about gravity, a force that has fascinated me for decades. Welcome to Mindshare Reports, Professor de Rahm. It's a great pleasure to have you.
Thank you very much. It's a great pleasure to be here.
We are almost into the 340th anniversary of Newton's 1687 formulation of the universal law of gravity, as well as the 111th anniversary of Einstein's 1915 theory of general relativity about gravity. Tell me your broad brushstrokes view of where we are in terms of understanding gravity.
111, that's beautiful. I never realized that. That's good. It's a nice year. It's almost more important than 100. We are a long way, in fact. We often emphasize the challenges with gravity, but how much we understand it, how precise it is, and how much we actually use it in our everyday life, in our everyday technology, is just mind-blowing. Just the fact that we are able to have this recording like that. You are in the US, you're in Chicago, I'm in the UK, in London. That goes through satellites, which understand, well, not the satellites, but for that to happen, we need to have a very precise understanding of the laws of gravity through the effect on the flow of space and time. And that works extremely well since we're talking together. So we've gone a really long way.
The idea of I'll come to the universality of gravity in a bit, but we are now at a stage where scientists like you think that the information about gravity has to be encoded into something more fundamental and deeper than us. These are your words. Say, into the very fabric of space-time. That sounds so mesmerizingly profound. Please explain.
Right. So we are used to understanding that if we have, for instance, a massive object being there, for instance, a planet, but that doesn't need to be a massive object only. But we used to understand that we are attracted by those other masses thanks to gravity. The way we understand this nowadays is the effect that those things, those masses, those energies have on the environment. And when we say they have on the environment, we don't mean on the air, on an electromagnetic field. We actually mean it has an effect on the way points in space and points in time are connected together. And that's really profound. It sounds like I'm just saying those words as a cartoon to give you an idea of what's going on, but it's not quite the real phenomenology. But in fact, this is really what is happening. We understand that if we have some masses present, if we have some energy present, then it affects how different points in space and time are connected together. So this is what really we mean by saying gravity is encoded in the fabric of space-time. That is an abstract concept, but what is less abstract and what we can actually measure is how we perceive the flow of time, for instance, how we perceive a notion of distance between 2 points. That is something very concrete. We can measure it, and then we can determine how this is affected by the presence of other things, which we would think have a gravitational effect on us. But in fact, the way they communicate that is through the effect they have on the curvature of space-time, on the fabric of space-time. And it's not that this object is directly affecting us by holding us in the hand, for instance. So the gravity is a force at a distance. It's not a contact force, but it indirectly affects us because it affects space-time, and we live on that space-time, and so we're experiencing this effect of masses and energy.
The way you're describing it, the fact that the gravity is intrinsic, in a sense, to the fabric of space-time, you're basically saying that the gravity itself, in a sense, it's the universe. If it is so deeply embedded in everything that we see and experience.
So yes, gravity is deeply embedded in our experience of reality. That's definitely true. And there's almost it almost goes the other way around. In our understanding of the notion of space and time is intertwined with our understanding of gravity. And so when there is a point where our understanding of the fundamental laws of nature, our understanding of gravity fails us, as it happens sometimes, then really it is our description of what we even mean by the notion of space and time which fails us.
Right. The idea of the universality of gravity and hence the universality of the laws of gravity had always fascinated me. How have we reached the determination that about the actual universality of gravity? Because our field of experiment is, in a sense, limited when you compare the size of the universe. Do you ever wonder that there may be pockets in the universe where the laws of gravity completely fail? I mean, there are obvious examples, but I would like you to give those.
Yeah, so we test that. We absolutely, when we have an observation, when we have an assumption, or when we have something which is ingrained in the laws of physics, in the way we understand the world around us, we keep on challenging ourselves. So you can think of a test of the universality of gravity in different ways, and we keep on doing those in a more and more precise way. In fact, I'm working at Imperial College at the moment, and we have some experiments between different kind of atomic clocks and the way they perceive the flow of time, depending on their internal structure, is being tested, and we see that that works really well. That's just an example. Now, the way there's different ways we can test the notion of universality, because universality is in fact universal in its universality. It's not only that different masses fall at the same rate. That's one of the understanding of the notion of universality. But it's also the fact that the way we feel gravity, or the way gravity affects us here on Earth, is the same as what it would. It's the same mechanism that describes the motion of planets in the solar system. And that's the same kind of mechanism, an underlying law of nature that describes the way galaxy got structured and the way the universe itself got structured. So it goes really from a universality of its mechanism from very small scales to very large scales. So now when you're thinking about the universality and challenging that universality of gravity, it's been done in different ways. One of the ways it's been done is testing different kind of components, different type of bodies, if it were, and determining whether all really are experiencing gravity in the same way. And this is the best test of universality. We have constraint on the equivalence principle and how gravity is equivalent for different things, or how the inertial mass of a body is the same as a gravitational mass of a body for different atoms. We have this universality, this equivalence in one part in 10 to the 15. So that's a very strong one.
Right.
In addition, we also have an understanding of the universality as a function of time throughout the cosmic history of the universe. And we know that gravity can't have behaved very differently in the beginning of the universe as compared to today. We have constraint on how different parameters can evolve as a function of time, for instance. And we also have a very strong constraint on the universality of gravity right here in the universe. So what I mean by that is a bit subtle, because when I compare different points in the universe, what I mean by today, in fact, when I look at things very far away, this is actually points which were very far in the past. but still we can adapt for that to some extent. And we do at the moment experience the laws of gravity in all intents and purposes to being the same at different places in the universe. So there's a very beautiful experiment which can now I'm trying to think, because you said it's 11 years since the direct detection of gravitational waves in 2015.
Correct.
In 2017, so just 2 years later, there was another, there's been multiple events, but there was another detection of gravitational waves that came from the merging of two neutron stars as opposed to two black holes. And so the beauty of that is when those two stars merged, they also emitted some light, some very high frequency light, which has been observed. And so we can compare the propagation of gravitational waves through millions of years to get to us. So they have traveled throughout some large regions of the universe to get to us. We can compare that with what happened with light. And that gives us another sort of handle on the universality of gravity, how different colors of gravitational waves travel and how they have traveled through different pockets of the universe, if you will.
Yeah. Tangentially, it is astonishing that a couple of minds, say Newton's or Einstein's, conceive of something so fundamental. Purely at the cerebral level, it's astonishing.
It really is. What I find astonishing is how gifted we are as human in actually being able to uncover the laws of nature. I have to admit, though, more and more, but it has been the case throughout history, even in the time of Newton, even in the time of Einstein, it's not that just someone came along and discovered everything by themselves.
Right.
We have to be ready. We have to have all the mathematical framework behind it to be ready to accept this concept. And so it really is a universal empowerment. It's not one person making a discovery, making a claim, and this going forward. It's really a whole group of people, but the whole society really being ready to adapt their perspective in a particular way and able to see the world through these particular lenses. And you need to have everything in place, all the structure that hold those theories in place for this to happen. You need to have all of the mathematical framework of understanding how to combine the notion of space and time together, for instance, what it means to have these levels of universalities and symmetries. All of this is not just Einstein that came up with it. All of that formalism, all of that structure was there at the time.
Indeed, indeed. At the level of people who do not practice science the way you do, for instance, which is the vast majority of the human race, gravity seems like almost like a non-existent thing. It's not even a force to most people in the way we understand the three other fundamental forces: electromagnetic, strong and weak nuclear forces. Why do you think that is?
So I think it is because of its universality, and it is actually true. It is actually true that we as humans are not really able to experience gravity per se, because it doesn't act on us in a way where ourselves are able to distinguish the effect of gravity. And so this is quite different as compared to electromagnetism, for instance, where we have a particular screen on the back of our eyes, which is able to detect the photons and able to distinguish between the different effects of the electromagnetic field. So we are able to separate out the effect of the electromagnetic field. Different cells in our body respond differently to it, and therefore we are able to feel it in some sense. And that's the way for the other contact forces as well. For the other fundamental forces of nature, but we don't really experience them in life. Our cells per se are not able to separate the effect of gravity. They all behave the same way through the gravitational attraction. And so really, to really appreciate gravity, we really need to look at different points in space and see the effect that gravity has on space in between those points. And so this is not something a body like ourselves is able to experience. So that's one reason. And then the other reason is because gravity is actually a very, very weak phenomenon. We may not think so here on Earth because the Earth is so humongous and it's so massive that in the end it has a big gravitational pull on us, and so we're stuck to the surface of the Earth and we can't go any lower. But if you just imagine if the Earth was, every atom in the Earth was electrically charged, just imagine the electric discharge, the static you would get from the Earth. So the reality is we don't really experience it, we think, in the same way as the other fundamental forces of nature because gravity is so weak.
Right.
Yeah.
That begs the question: is it then fair to gravity to call it's a run-of-the-mill force like the other three?
So calling someone a force shouldn't depend on how strong that force is. And in fact, we have a weak force, we have a strong force.
True.
So you shouldn't really take out the quality of being a force just because you're not very strong. That's okay. You can still be a force,
right,
even if you're not very strong. The reality is how you act on other things. That's really the notion of a fundamental force. And so for those aspects, gravity is very, very similar to electromagnetism.
Right. What do you think of a new theory that suggests that gravity could possibly be the result of entropy?
Yeah, so I have to admit, I don't think much about it. It's a very, very interesting idea. I like concrete things. And so for me, the step between this beautiful idea and making it concrete in ways we can actually test it, experiment with it, and really follow that through is still a little bit more challenging for me at the moment. So if I were able to follow that through and really see a clear link between this emerging notion of gravity and how we can actually use it to describe gravity in the same way as we want, in a different way, that would be a huge success, I would say.
Yeah, in the same way, what's your view of loop quantum gravity, the theory that space-time is not smooth but made of?
Yes. So we do know, and I think I would say, let me background a little bit. One of the beauty of Einstein's theory of relativity is that it also tells us that it's not a complete theory per se. The theory of Einstein gravity, which we'll call general relativity, predicts to some extent its own failure. And then we know that there are solutions to Einstein's theory of gravity. There are solutions to it where the curvature is so dense that we can no longer use that theory to describe what happens in those environments. And so we don't even need to go and test it and check that it doesn't work because the theory itself tells us that doesn't work. So we do know that we need to complete gravity. We need to complete Einstein's theory of general relativity in a way or another. And I think it's really important to keep our mind open and to try different perspectives. There are different classes of perspectives, and one of them is to try to make things which we thought were continuous, make them discrete. So there's a beautiful idea, which is not loop quantum gravity, but let me start with this, is instead of thinking that space itself is continuous, you can think that it's made out of discrete points. And so you can be here or you can be there. You can be at different points in space. You can be at different points in time. And that you need to understand how those different points in space and time are connected with one another. And so that's the notion of causal set. They are connected in a causal way. And you discretize space-time in that way. Causal set is one framework to try to understand how to think of the fabric of space-time and the gravity ultimately in a regime where we know the description from Einstein theory fails.
Right.
Another way to discretize things is not directly in space-time itself, but more in some surfaces, if you were. And so that's the idea behind loop quantum gravity. It's a little bit more subtle than that, but it's beautiful as well. And it's trying to quantize gravity in a different way, keeping some quantities discrete, like the surface or like the volume. So I think it is definitely a worthwhile endeavor. Mathematically, there are some challenges. Mathematically, we're making a lot of progress. It is true that still making the connection between those mathematical understanding of the laws of nature in that framework and the reality of the world in which we live is missing and still strongly missing. So we don't have that link, and so it's really difficult. People are trying to make progress, but it's in very simple, very unrealistic environment that really you can make that link.
Speaking of quantizing gravity, I've been thinking about gravitons. I'd once visualized a perfume called Graviton with the tagline that said, spray gravitas to yourself.
I see. I've never come across that. I should try it.
No, it's in my mind. I haven't made it yet. If I do, I'll send you the first bottle. So gravitons, are we still considering their existence or no longer?
I know the existence of gravitons is ubiquitous to gravity and to the quantum world. We can't work without them. It's not really a challenge to think of gravitons. In fact, it's a quite strong consensus that gravitons should exist. You may hear differently, but often it's it's people more on the margin that will say that the graviton doesn't exist. We don't really, no one really revendicates the absence of gravitons. When we think of gravity as a force, for instance, and we want to couple it to fields, we want to couple it to particles, let's say, which are quantum, like the electron. The electron, we know, satisfies some laws of quantum probability because the graviton communicates with gravity, they interact with one another. You cannot have the electron being a quantum system interacting with gravity, which would be purely classical, and then being able to go back to an electron. That would violate our understanding of the laws of quantum probability. So there's really little room for having any other thing than gravity being ultimately a quantum phenomenon. And there's absolutely no issue with that. In fact, this has been known for I would say, almost 20 years, how to think of gravity as a quantum field theory from the work of Pauli, for instance, who's one of the fathers of quantum mechanics. He very much thought about gravity as a quantum field theory. So there's absolutely no issue there. The issue is really thinking about quantum gravity at very high energy scales in very dense environments, like at the very center of black holes or at the very beginning of the universe, when there's so many gravitons all around that maybe they become a phase of something else. That's really what it's about.
Right. Do you believe there is actual propagation of gravity, or because it's so pervasive across the universe, it doesn't need to propagate the way, say, light does? That means it's not bound by the speed of light restriction.
No, it does. So it does. We have detected gravitational waves, and those gravitational waves are made out of gravitons. In the same way as light is made out of photons.
Okay, so then those rules apply to it, yes.
Yes, yeah.
Do you, I mean, I'm jumping themes because that's deliberate. I hope you don't mind it.
That's okay.
Do you ever wonder about the role gravity likely plays in the way life evolves across the universe? For instance, I seriously wonder whether life on Earth and life on, say, for instance, Jupiter's moon Europa or Saturn's moon Enceladus will be extremely different anatomically. I mean, we are what we are because of the way Earth's gravity is, isn't that?
Oh, absolutely. And we already know that we would have things evolved quite differently if they are in zero gravity environment. We adapt very rapidly to our environment, but we would definitely not have been the way we are if our environment would have been different, and therefore if gravity would have been different. That is for sure. There's like a Goldilocks, the right middle of the right balance that we need to have. Now, whether that means that life could only evolve on planets, life could only evolve in particular gravitational conditions, I think that is really hard to tell. I think we are typically bounded to imagine things in a way that we used to, but who knows, maybe life can be very different. Life doesn't need to be baryonic in the same way as the way we are. And so it's very challenging for us to even appreciate what it would mean, but it doesn't mean that it doesn't exist. It doesn't mean that it's not real.
One of the many themes of my book is to speculate, to wonder, almost in a silly fashion. Say things like, if we are able to talk or sing or play instruments or do whatever on this planet, is entirely a consequence of the kind of gravity that exists here.
Absolutely.
For instance, to play the accordion on the moon or some other body would be very different, if at all it's possible. I'm not sure. How do you look at things like that? I know it's perhaps sounds silly to a scientist, but I'm very curious because it seems
interesting. Yeah. I mean, that's really interesting. I guess you can play instruments on on the International Space Station, and they still
okay.
Some will still work. No, but it has an effect on everything. So I mean, there's different aspects to gravity there. There is the way we are experiencing it, and the way it also affects everything else. So one of the beautiful analogies, for instance, the tidal forces, the tidal forces of the moon, and we know that has an effect on everything from all of the affected, to some extent, not quite the season, but it does changes the rhythm on Earth in an incredible way. And that's just gravity, is just the effect of the moon on Earth, and it's been regulated in all of the actual cultures, in all of the actual way of thinking, in all of our art and architecture and everything. So it's really ingrained far deeper than we even can think about it. On a single day, we can't really tell. I wouldn't be able to tell what is the phase of the moon right now, but it does affect us, and it does affect not only us as human, but our whole ecosystem in a very ingrained way.
Right. This has nothing to do with the main subject of our conversation, but I want your help to resolve a question I've grappled with for 50 years now, since I was a teenager. I'm 65 now. Imagine a situation: there is a fly trapped in a spaceship going to Mars. Now, also imagine that the fly doesn't sit down even for a moment. It keeps fluttering around throughout the flight. Does it mean the fly actually flew those many miles? I'm not able to resolve this.
So what is happening there is that the space station, or what the spacecraft is actually pushing the air. So it is actually living in that environment where it's been pushed, and so indirectly that has an effect on the fly itself. If you were thinking that it's just hanging there at the beginning, it's going to be pushed. It was going to go down to the floor of the space rocket, if you were.
Right.
So there's an effect there, and so that effect translates into the fly itself is moving. As soon as there's an acceleration, and it will feel that because it will affect the flow of the air, and it will affect the fly itself. It will have to adapt for it. There will be a little bit of a wind to start with, or if it's very strong, then it will hit the bottom of the spacecraft. Every time there's an acceleration, there's a change, which means that the fly is actually undergoing something.
Right. What do you think about the impact of the ever-expanding universe on gravity as a force?
So I think it's hard to say the impact on it, as opposed to gravity itself is what has an impact on the expanded or the accelerated expansion of the universe. It's a little bit chicken and egg. perhaps another way to say that is because the universe is expanding, we may start thinking about how gravity behaves on larger and larger distances. And so this is possibly one of the areas of research I'm looking at. And so it's not that the expansion of the universe necessarily has an effect on gravity, but because we are exploring those questions, we are also exploring the question of what is gravity on those different environments. And as the universe expands, if it does cool down, if in the end it expands slower and slower, then we are forced to experience or to test gravity in a different environment. And that is going back to the question you had at the very beginning. We test gravity in all possible situations, but if there are situations we never experienced before, we simply haven't been able to test it there.
Yeah. No, but if gravity is a consequence of massive objects like stars and planets warping or distorting space-time fabric, if the objects are going further and further apart, wouldn't that weaken eventually gravity to a level where it perhaps may not even exist?
Yeah, so I would say gravity always exists, but the gravitational pull would be smaller and smaller. And that's what we had anticipated some 30 years ago. That's what we anticipated, that the universe is expanding. And so the distance between all of those massive objects is decreasing and decreasing. And therefore, their gravitational pull is becoming smaller and smaller. And so the way we express that is saying the curvature is becoming smaller and smaller. And so it looks like flat space-time. That's what we thought should be happening. But in fact, what we have observed in the past 25 years is not that. It's exactly the opposite. And that tells us that, in fact, there must be something else out there than just the masses of all of those stars and galaxies and clouds of dark matter. There must be something else that drives some expansion of the universe, that drives an accelerated expansion of the universe. And this is coming from the fact that it's not only, because of the universality, it's not only masses that have an effect on space-time. It's not, I have an effect on space-time, you have an effect on space-time, but light itself, which has no mass, still exists. And so there's an element there of universality where it wouldn't be fair to say because we have a mass, we have an effect on space-time, but light doesn't. Light does. Anything that in fact has energy, even if it has no mass, has an effect on space-time. So you can have just energy, which is not localized anywhere. It's what we can call radiation, a kind of radiation or a kind of dark energy. And that dark energy is what we believe leads to the accelerated expansion of the universe. And so it's not that, in fact, gravity is becoming weaker and weaker. What we do see is that there seems to be more and more and more of it, and we see exactly the opposite. So even though all of the massive objects, like the galaxies, are going further and further away from one another, what's in between is not just being dissolved. There's more and more and more of that thing in between, which we don't observe directly with our eyes, but we do feel gravitationally through the instruments. We do see the effect of that on other stars, on other galaxies.
Right. Just last three things. One is in the context of the idea of multiverse or parallel universes. Since our universe has its collective mass, would it not exercise any gravitational influence on our neighboring universes?
Yeah, so it depends a little bit what notion of multiverse and parallel universe you have. There's different things out there. One of the things you may think about is extra dimensions, and we can be living just in a surface on a bigger dimensional world. And so our universe is just some of those dimensions, but not the rest. And that's a little bit as if you're thinking of these animals on the surface of a pond, the water walkers. They just live on the surface of the pond, and they're not able to experience the depth of the water. And every so often they get eaten by a fish that for them came out of nowhere, because it's not living on the surface, it's just coming out of nowhere. So every so often there may be an effect that is coming from the extra dimension, but it's not visible for us on our surface. So if you're thinking of parallel universes, if you were, where those parallel universes, there are other surfaces in some extra dimensions, then absolutely we would have a gravitational effect on those. And in fact, one of my colleagues I was doing my PhD with him at the same time, he was looking exactly at that, is if you have a black hole on in a universe and there may be another parallel universe, there may be another black hole in that, and they may get attracted to each other a little bit. So that can
waiting for all you know. So
so these are just questions one can ask oneself. When people talk about multiverse, sometimes they have something a little bit different in mind, where they're not different parallel universe in the same representation of reality, where they localized in different places in an extra dimension. They are just different realization of reality. And so there's no notion of space and time in between. They're just different realizations. Something could happen, something else could happen, and they're not, and different realization of universe can pop out in and out from different in different ways, but it's not like they're connected necessarily by space-time, and therefore you can feel the effect on one another, or not in quite a similar way. It will be much more subtle than that.
Right. You know, in all the visual representations of the fabric of space-time, it is shown like a sort of a sheet, and objects distort particular areas.
Yes.
Now, this question again may sound utterly ignorant or silly, but I'm going to ask nevertheless, because it's been, again, troubling me for a long time. I know there is no notion of up and down in space, but nevertheless, if this is the sheet and there is an object here, what is above it or below it? Is it just the sheet, or it's the whole reality is space-time?
It's the whole reality. We just, it's hard for us to draw things in 4 dimensions. So it's not like there's something above or below. It's not like it's just in 2 dimensions things are distorted, and then in the up and down direction things are fine. It's just a representation. It's just we do an analogy when we draw that sheet. We sort of draw an analogy because we have a very good intuition of how things are affected by the gravitational pull of the Earth. That's what we're experiencing. Now, what we want to represent in those pictures of gravity with the sheet and then the ball is not the effect of the Earth. That's not what we want to represent, but we sort of can draw it in a similar way, and then we can draw an analogy with those two things. That's all. But you have to take that out of context, and it's not like there is an up and a down. The only thing you should take out of it, which is real, is the fact that there is a curvature at a given point, which is the closer you are to that mass, the more curvature there will be. Right. The way you will identify this curvature is a bit different as compared to what you would do in the sheet. The sheet may be quite different, but there's still some notion of curvature. It affects more the curvature of space-time closer to the mass in a sort of similar way. That's all.
Okay. To conclude, I'm going to ask a question which I always ask all physicists who come to my show.
Yes.
It's perhaps in the philosophical realm, but I'm going to quote the Nobel laureate, the great Nobel laureate Steven Weinberg, who very famously said in his classic book, The First 3 Minutes, and I'm quoting him now, the more the universe seems comprehensible, the more it also seems pointless. That's a brilliant quote. I know as a scientist, you do not look for purpose or meaning to the universe. Even I don't. But how do you grapple with this philosophical question? At some point, it must be troubling you. What the hell is this? I mean, what is it trying to tell us?
Well, I mean, for me, when it comes to those points, it's really it's almost the opposite. I feel happy because in fact, it's such a privilege to be living in this universe. We are so lucky in so many different ways, because really, by all means, it shouldn't be like that. It would be so much simpler if everything was nothing. Nothing is always a solution, and it's always the simplest possible way to do things. And so the fact that the universe even got to exist, so that's a mystery, but it even got to be in the state it is today and evolve in that particular way, let alone creating galaxies and creating stars and creating an Earth where we can live, and let alone
There was a big break in between.
okay.
No, that's okay.
Yeah, you want me to restart?
No, I got the gist of it. Yes.
Okay.
Okay.
Sorry.
Final observation, because how do you look at Professor Penrose's conformal cyclic cosmology? It is fascinating because I'll tell you, coming from India the way I do, he makes a specific reference, which is rather rare for a scientist to say. He said it's in some ways it's like Hindu philosophy, which is basically saying that there is no beginning, there is no end. It's just a continuous process.
Yes. So there's definitely a beauty there, and it would resolve a lot of our problems. Using conformal symmetry to saying that when you get roughly, of course, I'm not quoting it the way he would want to, but when you go into very small scales, then in fact, then there's a symmetry, and you can go to very large scales, and you'll be able to do a relation between the two. This is fine, but I think it's still not addressing the fundamental problem, because you would expect things to break down at some point. I think there's still some unresolved unknown which haven't been addressed. So I'm not saying that is not potentially relevant, and it most certainly is relevant, and it probably holds some level of what is happening, but really being able for us to use this and understand how it will actually addresses the singularity is something, at least for me, is not resolved. So he wants to say there's no singularity, which is fine, but you need a little bit more than that.
That's right. Yeah. On that note, Professor de Rahm, I really want to thank you for your time. It was riveting for me to talk to you. I hope it was worth your while. I'm going to